Morning, everybody.
Morning.
Thank you. The reminder to get your quiz sheets into me if you haven't already. I've already started inputting those quiz grades into Canvas. The quiz grades will revert to 0 as we get closer to the 4th exam, so make sure that you get that in there. I think that's kind of all the announcements and business that I had to conduct. The instructions will come back up at the end of class in case you didn't see them yesterday. All right. Chapter today. No problem.
Chapter today.
Okay. We might actually get started on chapter 15 because I'm cutting material left and right. So especially for this unit. This has been semi-true for the other units, but especially for this unit, if I haven't talked about it in class, you don't need, if it's not on the homework and I haven't talked about it, you're not responsible for it. Okay? It's just, I'm just cutting out so many things. Like today, we're supposed to go over kinetic theory, and I can't think of something that's more boring than kinetic theory. So we're going to go over it, but really fast, and we're not going to do very many calculations, all that kind of stuff. So take a cue from me as to what the expectations are. But what we're going to do today is we're going to try and talk about the ideal gas law. And everything associated with that. And to get there, we do need to talk about moles. Okay? Now, if you've had chemistry, then you know hopefully what a mole is, right? What's a mole?
Avogadro's number or something.
Avogadro's number or something? Who the heck? No, let's not answer that question. What's the number?
6.022 times 10 to the 23rd.
So you guys obviously have been abused enough with chemistry, okay? So what unit goes on here? 1 mole is equal to 6.0022 times 10 to the 23 watts, right? Like quants. Okay? So for some reason, people get tripped up on, I think, on how big the number is. So you need to think of the mole like the chemist's dozen. So what does the word dozen mean? 12. If I get a dozen donuts, I get 12 donuts, right? What's a baker's dozen?
13.
It's 13 because bakers can't count or something. I don't know what to do. Yeah, okay. So we have these words that mean a certain number of things, or like the 1 dozen means 12. That's what the mole is, okay? So when I say I have a mole of carbon atoms, how many carbon atoms am I talking about? That many, okay? It's just because atoms are so small and molecules are so small, it's a little bit advantageous to kind of scale things around. This is always a fun thing to do. It's about the funnest part of this whole chapter. How big is that number? Okay. You guys totally underestimated how big that number is. Yeah. But that's human, okay? As humans, we really struggle with numbers that are bigger than 100 when it comes to our concept of things, right? If I said that if I had 10 basketballs, right? You'd have a pretty good idea of how many, what size, the number of basketballs I have. Even maybe 100 basketballs. But as soon as I say 1,000 basketballs, you start losing the ability to realize how many that is. If we go to 10,000 basketballs, you have no, can 10,000 basketballs fill this room? Could it fill several gyms? Like, we lose the ability really after 100 of anything, okay, to really conceive of how much of a thing it is. If you had a mole's worth of basketballs, how much space would you need to hold them? You'd need the volume of the earth, okay? It's a lot of basketballs, okay? This has always been one of my favorites. I wrote down several of these. Unpopped popcorn kernels. So if you just had a mole's worth of unpopped popcorn kernels, to what depth if you evenly distributed, you poured out all those popcorn kernels all over the continental United States, so not Alaska and Hawaii, okay? You just filled the United States with popcorn kernels. How deep do you think it might go? If you have 1 mole. 20 miles? It's actually 9 miles, right? Okay, but still 9 miles of popcorn kernels above your head, right? That's higher than Mount Everest, right? Pick dollar bills or donuts. Donuts? 1 mole of donuts. Okay? What if we distributed 1 mole of donuts over the entire surface area of the earth? How deep would we be in donuts? Cover all the oceans, all the land, everything.
5 miles.
It's 5 miles. It's 8 kilometers. Okay? I guess it depends on if it's Krispy Kreme. Because if it's Krispy Kreme, they'll start crushing under their own. If I had 1 mole of dollar bills, and I evenly distributed that money to every man, woman, and child in the United States, everybody in the United States would be a trillionaire. Everyone would be 1 trillion times more rich than Elon Musk. That's how big a mole, like it's mind-bogglingly big how big that number is, right? It also kind of describes really how small molecules and atoms really are. Because a mole's worth of carbon, we don't have, I hate this room, we don't have a periodic table in it, okay? But carbon on the periodic, I've got a periodic table right here. Yeah, there we go, okay? Let's clean it up. Okay, so a mole's worth of carbon. Carbon right here, you can't see it, but the atomic mass says 12.011. So, carbon with its 12.011 atomic mass units, okay? How much carbon do we need to have 1 mole's worth of carbon? The answer is 12 grams. The atomic mass of any element is the amount in grams that you need to have 1 mole of that thing. So oxygen has an atomic mass of 16. Okay? So how many grams of oxygen do we need to have? Wait for it. So oxygen is like 15.999 whatever, okay? Right? So how much oxygen gas do we need to have a mole's worth of oxygen gas?
16.
It's not 16. It's 32.
Oh,
Because oxygen gas is O2, right? And so 16 times 2 is 32. So if we had 32 grams of oxygen gas, we'd have 6.022 times 10 to the 23 molecules of O2. So whenever you see an atomic mass, you can just put grams on that, and that is the weight of stuff that you need in order to have that many moles of it. 1 mole equals that many grams. Okay. What else do I need to tell you about moles? I don't think there's anything else to tell you about moles. Brown furry creatures that dig in the dirt. Okay. Ideal gas law.
TV's equal to NRG.
Yeah, I know. It's that equation. Okay. But for some reason, chemists try to make this too hard.
I agree.
Okay. There's they take their time. Did you guys ever learn like Boyles's law and Charles's law?
Yeah.
Okay. I don't understand why they do all. I mean, historical reasons. But like, all those laws are in this one. This one summarizes all of the relationships, say, between temperature and volume, or pressure and volume, and all that kind of stuff. So if we look at the ideal gas law, first of all, what's an ideal gas?
Yes, under ideal conditions.
Gas under ideal, no. It's a gas that behaves itself. That didn't help either, right? Okay. There's certain definitions for what an ideal gas is. Things like it doesn't liquefy when it gets too cold, right? it stays a gas no matter what temperature it is. It's a mathematical ideal, okay? They're usually monatomic. There's like, it always obeys Newton's laws, all these different kinds of things. Actual gas molecules are kind of ideal gases. Like air, oxygen, nitrogen, all of these gases are ideal gases as long as we don't make them too hot or too cold. So the ideal gas law is an excellent approximation for normal everyday gases like the gas in this room. Okay? As soon as we liquefy a glass, as soon as we pressurize it and it becomes a different state, then the ideal gas law kind of goes out the window. But we'll assume all of the gases we deal with are going to be ideal gases just to make our life simple. But what happens to the, okay. Volume, pressure, temperature, right? The thing here in the front, the N times the R is typically a constant, okay? The R is definitely a constant, okay? It's called the gas constant. You are going to hate life because in physics, this is 8.31 joules per mole Kelvin. In chemistry, I did this one for you. This is just for you chemists. Liter atmospheres per mole Kelvin. Okay? So that might be the one that you're used to from chemistry. Okay? Because it's scaled for liters and atmospheres already. Okay? In physics, we use 8.31 joules per mole Kelvin. Which means that your pressure unit better be what? Think SI units.
Pascals.
It better be pascals. Your volume better be what?
Liters.
Cubic meters. Not liters, cubic meters. Liters is not an SI unit. Okay? And then temperature has to be in Kelvin for this to work. So when you're dealing with the ideal, so when we did calorimetry, it didn't matter if it was Kelvin or Celsius, because we were always talking about changes in temperature, and that delta saved us. But when we're doing the ideal gas law, your temperatures have to be in Kelvin. And how do you convert from Celsius to Kelvin?
273.15.
Yeah, you take your temperature in Celsius and you add 273.15 degrees, okay? So just make sure that you're careful. Use 8.31 in this class. Make your pressures in pascals, your volumes in cubic meters, and your temperatures in Kelvin. You'll be okay. More importantly, though, if we say keep the volume constant, we're not going to change the volume. Okay? What happens to the pressure if the temperature goes up? It also increases. See how they're on opposite sides of the equal sign? Okay? If we keep the temperature the same and the volume decreases, what happens to the pressure? It increases. See, they're on the same side of the equal sign. So things on the same side of the equal sign will be inverses of each other. But things on opposite sides of equal signs will be in lockstep with each other. If they go up, they both go up. If they go down, they both go down. So what the ideal gas law is, it's an equation of state. The states of pressure, volume, temperature. Those are state variables. They're things that we can actually measure about the gas. And the ideal gas law is a way to bring everything we know about how gases act into one concise formula. Charles's law, Boyle's law, they were all stepping stones getting to the ideal gas law. I can't remember which ones it was. Charles's law about volume and pressure, temperature, I don't care. Okay? But like the ideal gas law kind of sums it all up. Okay? So let's do some ideal gas law. I hope it's not that hard. You're just solving an equation and chucking stuff in. This is not my idea of a fun time. Okay. So let's see what's going on here. Oh, sorry. What's the N on the front here? Yeah, this is the number of moles. That's why we're talking about moles. Number of moles of the gas. Okay. All right. Okay, so here we go. Lucky for us, they gave us the volume in cubic meters. That's nice, right? They gave me the temperature in Kelvin. How nice! I must have written this one because all the units are consistent. I don't go out of my way to like say, whoa, the pressure is 64 torr. They're going to have to convert. Anyway, so what are we looking for? We've got to visualize, strategize, do it, check it. What in our visualization, what are we being asked to find? There's the key word, find. Find the number of moles. In the ideal gas law, what are we looking for?
N.
We want that N right there, don't we? So as part of my visualization, I think I'm just going to solve for N. That's going to be pressure times volume divided by the gas constant times temperature, right? What do they want to know? The number of moles, I got it, to increase the pressure. Okay. So in order to increase the pressure of a tire, to inflate the tire, what do? You put more gas in it, right? Okay. So what we're looking for is the increase. How many number of moles? So if we start with 15 moles in the tire and we go to 20 moles in the tire, what was the amount we had to add? 5. That's what they're asking us to do, right? So that suggests that I need to calculate the number of moles we have to begin with, and then the number of moles we have at the end, and then take the difference, right? So let's see where that gets us. That means that I have to have like an initial number of moles, which will be the initial pressure, the initial volume. Gas constant is just the gas constant times temperature initial. And then I have to have a final version of that. And I can do this now, right? So pressure. Pressure initial. 212? 212,000. So 212 kilopascals. What does kilo mean? Times 10 to the 3. And then my volume they gave me, 0.0185 cubic meters. Gas constant, which one am I going to put in? Good, 8.31, the more perfect one. And then what's the temperature? 294. Okay. All right, so that will be my initial, and I think I did this. This turns out to be 1.61 moles. Now, how did I know it came out in moles? What numbers went in? SI units of pascals, cubic meters, kelvins. So that guarantees that if I'm solving for moles, that I'll get moles out. Because the equations, no, they're dimensionally consistent. Okay, so final. Pressure final, 252 times 10 to the 3. Uh-oh. Do I know what the final temperature is?
Constant.
So they remain constant, meaning it's the same, right? Before and after. So this is going to be, the volume stays the same, because it says volume and temperature, right? 0.0185. Now that's not strictly true. Your car tire does change its volume a little bit while you inflate it, but we're pretending that it doesn't. 8.31 and then 294, right? So then I got 1.91 moles. So what's the answer? Is that 0.3? I think that's 0.3, isn't it?
Yeah.
Yeah. What's the trick? Or what do you need to be careful of? Units, right? Especially if you've been in chemistry, there is this pull to want to do everything in atmospheres and liters, which is fine. If you do it in atmosphere liters, what are you going to use for your constant? The other one, right? And I will not, well, I might think bad thoughts about you, but I won't say anything, right? But if you do that on a test, it won't, as long as you get the correct answer, right? It doesn't matter if you use the chemistry units or the physics units. I can do units. I'm a big boy. I can do units. I just don't like using anything that's not SI units. There's another way that physicists especially like to use the ideal gas law. And a lot of times, especially in situations where physicists are interested in what's going on, we're actually not doing anything with the number of moles of gas. Like the system is closed and we're not letting gas in, we're not letting gas out. It's the number of moles of gas in whatever container we've got is constant. If that's true, and this is an example of a problem where that is true, then we essentially have two states, right? We've got P1V1 equals nRT1. And we have P2V2 equals nRT2. There's something that's identical between those two equations. What is it? nR. So if we solve both of them for the number of moles times the gas constant, in a problem where the number of moles isn't changing, then we can just simply write P1V1 over T1 equals P2V2 over T2, and we're good to go. This form of the ideal gas law is the one that physicists reached for first. We actually don't do PV equals nRT unless, well, we'll do it if we're forced to. But in physics systems, again, the systems that a physicist would more than likely study, we are concerned with pressure, volume, and temperature, but we usually keep the amount of gas in the system constant. And that's what's happening here, right? So how do you know that the number of moles isn't changing? So the balloon, right, has gas in it at a certain temperature and pressure, okay? We're changing the temperature, and we're asking what the volume, what happens to the volume? Did it mention anything about the amount of gas in the balloon? No, we could find it, right? If we know the volume and all that, right? We could find it. But what's sort of one of the defining characteristics of a balloon? It's closed, right? It keeps the same amount of gas. Now, okay. I know, because I think one of the saddest thing in a child's life is that day that you realize that your helium balloon leaks. Right? It worked so good the day before, and now it's sad on the ground, dying. It's like a child's first experience with the existential dread of adulthood, right? And so, yes, I get it. Gas leaks out of a balloon normally. Latex can't hold on to helium, all that kind of stuff. But these are ideal gases. And so it's going to be an ideal balloon. And everybody's going to be happy. And every child's going to be happy. And adults can be happy. Okay, so how do I pull this off? Since the number of moles of gas is the same and the gas constant's the same, actually I don't have to worry about it. But I do have these two different states, right? Like volume 1, they sort of tell me right here. Volume 1 was 3 liters. Uh-oh. And the temperature was 87 Kelvin, pretty cold. And the pressure was 101 times 10 to the 3 pascals. I'll just do the conversion right now. Okay. I'm going to have to do something with these units, aren't I? Let's put that on the back burner for now. Yeah, I know. In all truth, I did write this one too. So this is me being a little bit mean. But you're up to it. You're smart. You can do this. I've trained you well. All right. So V2. Do we know what the volume will be after the changes take place? Does the problem tell us what the volume is? No, but what is the problem asking us to do? What's the new volume, right? So this is what we're after. Okay. Do I know the temperature? Sorry, T2. It's 23 Celsius. Oh. Mr. Balogh's being mean again. Okay. What's the pressure?
Constant.
It's constant, right? So it's the same as what we, right? So nothing's changing there. Okay. So we need to solve the thing in the black box for V2, which for some reason I put a T on it. V2, whoops, black, V2. All right, so we need to solve the thing in the box for V2. The thing is, though, I have P1 V1 over T1 equals P2 V2 over T2. P1 and P2 are the same, so what happens?
Cancel.
Nice. So V1 times T2 over T1 is equal to V2. I multiply both sides by T2. Right there. Okay. Do I know what my volume 1 is?
Yeah.
Yes. Do I know my temperature 2?
Yeah.
Yes. Do I know my temperature 1?
Yes.
So I can just throw the numbers in and go?
No.
No. What's the problem? Units are all messed up. Okay? But there's only one unit that I have to change.
Yeah. Liters.
Nope. If I'm going to divide two things into each other, what do I have to make sure they are? The same unit. If I'm going to add or subtract or divide, I have to have the same units. Multiplication gets weird. You can have different units. Okay? But addition, subtraction, division, got to be dividing by the apples by apples, right? Otherwise, weird stuff starts to happen. Okay? So, I can put 3 liters into the volume. I'll get liters back out. And annoyingly, like Wiley Plus is probably going to want liters, or it'll probably want like cubic parsecs or some weird unit that like makes no sense, right? Okay. Times. I keep threatening I'm going to write my own Wiley Plus. But I'm not, I don't like coding. I can do it. And everybody's like, well, just vibe code now, Mr. Bailey. I'm not going to vibe code. Okay? The problem with writing systems like Wiley Plus or writing your own textbook is that you become a slave to the textbook and the system for the rest of your life, because everybody will expect you to maintain it and upgrade it and probably put AI in it and a storefront and sell T-shirts and merch. And I just don't want to do it. T2. What's T2? I can't remember. What was I doing? I'm trying not to do the ideal gas law. Can you tell?
296.15.
It's 23 Celsius, and then T1 was 87 Kelvin. So what do I need to do here? I've got to fix one of them, right? Brandon over here says he wants to fix the Celsius one. So it's 23 plus 273.1. You can drop the 1.5 if you want.
No.
Yep. Okay. So there, by converting the Celsius into Kelvin, sort of in the equation right there, right? The Kelvin and Kelvin will cancel each other out. I get the correct ratio, and then I can just multiply by whatever volume. By the way, how do you go from liters to cubic meters? A liter is 1/1000th of a cubic meter. A liter is 1,000 cubic centimeters, I believe is the conversion. Okay? And that's equal to 0.001 cubic meters. 0.00 tens, hundreds, thousands, yes. Okay? Anyway. Not too hard. Well, hard because it's just moving decimal points around. What's this answer? 10.2 liters. So, let's check, right? 4-step, check it. What happened to the temperature? Go up or down? It went from 87 Kelvin to 23 Celsius. But 23 Celsius plus 207, that's 293 Kelvin, isn't it? So it went from 87 to 290-ish Kelvin. So the temperature of this gas went up. What's going to happen to the volume if you keep the pressure the same? What's the ideal gas law say? If the pressure stays the same, volume and temperature are on opposite sides of the equal sign. If temperature goes up, what happens to the volume? It goes up. What's that?
Oh, then that's what we saw.
We got a bigger number, so I'm happy with that. As this physicist would be more than happy with that answer. Even if it was in liters, I'd be like, fine, liters. We started with liters, we end in liters. All right. All right. Kinetic theory of gases. This, I got tortured with a whole semester of this. In physics, we call this statistical mechanics. And it's as bad as it sounds. Okay? Imagine taking everything that you've learned in this class and then using statistics to solve problems that involve lots of tennis balls or basketballs or elements of a gas or something like that. It can be very tricky when you have a gas and you've got lots of molecules in it to say specifically what one molecule is doing. And so instead, you apply statistics to your population. And like I said, it's like this class mixed with statistics class. It's a nightmare. So we're going to do kinetic theory of gases slightly different. We're not going to go through all that statistics. I'm going to give you the punchlines because there are a couple of important punchlines that come out of this approach to trying to understand how gases work. The kinetic theory of gases. Kinetic, what does it mean? Moving, right? So the kinetic theory of gases models a gas as a bunch of little billiard balls bouncing around, moving all the time. The really kind of neat thing is you learn stuff like how fast a molecule of air goes based on its temperature. It's actually moving pretty fast, right? So we can calculate all that kind of stuff. The kinetic theory makes some assumptions. It says you're going to have a large number of molecules in your gas. This doesn't work if you only have one or two molecules in your gas. It obeys Newton's laws. There's no excess forces beyond the interactions that they have. So there's no like van der Waals forces or other long-range forces. Every collision is perfectly elastic. And all the molecules in the sample are identical. So these are kind of like, they seem like oversimplifications, but it turns out that real gases are a really close approximation to this. So there's little tiny differences, but for the most part, we get a lot of predictive power out of what's going on. One of the things that we get out of the kinetic theory is an equation for the average kinetic energy of a molecule in a gas. And you'd think that if you took statistics and you threw it at physics and they got together and produced something, it would be awful. And you're not wrong. But this turns out to be pretty darned simple. It's equal to it's equal to 3 halves, not 1/2, 3 halves, times a constant called Boltzmann's constant. Okay? Boltzmann's constant is a number. It's 1.38 times 10 to the minus 23 joules per Kelvin. So you just write that down and don't worry about it. Okay? Times, and there's only one other thing here. Temperature. Remember when we started a couple chapters ago and I asked you what's the difference between total energy, temperature, and heat? What did temperature end up being? Measure of the average kinetic energy of a molecule in a material. And so that's how we know what temperature is. It comes out of the kinetic theory of gases. I think it's actually quite astounding and elegant that something so bad as statistical mechanics can produce a very straightforward and simple relationship between the kinetic energy that gas molecules have and their temperatures. Notice there's nothing in here about pressure, volume, number of moles of the gas. All of that matters because an ideal gas obeys kinetic theory. So I can find out, if I know what the pressure and volume is, I can find the temperature and then from that temperature find the average kinetic energy. There's another way that you can write this exact thing, okay? And it's written in terms of sort of what we would consider the kinetic energy to be, because we wrote down kinetic energy before as what? 1/2 mv squared, right? Okay. So there's a little bit of, I'm going to add something to this equation here in a second. There's a little bit of a problem if we try to sort of blindly calculate the kinetic energy of a gas molecule. And this is the problem. For all the gas molecules in this room, for every single one of them that might be moving to the right, there's probably another one that's moving to the left. And for every one that's going up, there's one going down. How do I know this? How do I know that the velocities, so magnitude and direction, are all evenly distributed? Because the air isn't going anywhere, right? The average kinetic energy of the air in this room is 0. If it wasn't, we'd feel the breeze, we'd feel the wind, we'd feel it going somewhere, okay? So how do you take an average for something whose average is 0? Well, the answer is you cheat, okay? And you cheat using something called statistics. Statistics is lying with numbers, okay? So the way that you pull this off is you use something called the root mean square value, or the RMS value for the velocity. What the heck is that, and what is going on? VRMS, the root mean square. Okay, so root, what symbol is that going to be? That's a square root, right? What's a mean in statistics? The average. And square is a square it. So what you do, if you have a situation where your average velocity is going to be 0, because you have so many molecules and they're all going in all their directions, they're all going to add up to 0 anyway, is the first thing you do is you square it. What does that do to like all of your data? You got positive data, negative data, they're canceling each other out. But now if you square all your individual pieces of data, what's every single piece of data going to have for a sign? It's going to be positive, right? So now that everything's positive, you can go ahead and take the average, or the mean. But now your average is inflated, isn't it? You've squared everything to get rid of the minus signs, but now your average is too high. So what are you going to do to fix it? This is statistics. It's part of statistics. This is how you get around things that have an average of 0. It's called taking the root mean square. You'll encounter this again in physics 2b. Whenever we have something where the average is 0, we go, okay, fine. The average is 0, but the root mean square value isn't. And then we can go off and do some more predictive power. So just watch out for that. That's what that little RMS means. It means root mean square. And it basically means we've allowed statistics into the room. And we kind of have to deal with it. Okay? So the kind of the neat sort of thing that you can do with this, right, is if you know the temperature, you know the average kinetic energy, don't you? So if you know the temperature, you can find the velocity. Hydrogen, I calculated this out. VRMS comes in different versions, okay? You can either do it as 3 times Boltzmann's constant times the temperature divided by little m, where little m is an individual mass of the molecule or element. Or you can use 3 gas constant, physics version, temperature divided by capital M, where capital M is the molar mass. It's the mass of 1 mole of the element. Either way, you'll get the same answer. For hydrogen, this number turns out to be about 2,000 meters per second. 2 kilometers per second. So if you had hydrogen gas at room temperature, an individual molecule will be moving at 2 kilometers per second. If we go back to our orbital dynamics, you may or may not remember, but to orbit the International Space Station, we needed about 7.5 kilometers per second, right? So a hydrogen molecule on the surface of the Earth at room temperature is moving essentially 1/4 the speed it needs to get into orbit. What happens to the temperature of molecules as you go up through the Earth's atmosphere? It gets colder until it doesn't. Until you hit something called the thermosphere. At the thermosphere, you abruptly change this decreasing temperature and you get really hot really fast. 500-600 Kelvin in the thermosphere. Okay? So what happens there is gas molecules like hydrogen or helium, because of their low masses, do you see how the mass is in the denominator? Right? The smaller that is, the bigger your VRMS for a given temperature. You can get hydrogen and helium to achieve escape velocity. Escape velocity of Earth is 11.2 kilometers per second. And at 500-600 Kelvin, these molecules can easily exceed that. So why doesn't Earth's atmosphere have a lot of helium in it? And when you take a breath, you're not taking in hardly any helium or hydrogen. It's escaped. A lot of it's escaped, okay? Or it's in some clown's party balloon somewhere, okay? But our atmosphere does consist of nitrogen, oxygen, argon, 1%, and then like a smattering of other things. It's the other things, by the way, that you never want to look up because it'll just scare you. Why are those gases still around? They have bigger molar masses, they have bigger mass per molecule, and so they need more temperature to get to escape velocity, and they can't achieve it. Even in the thermosphere, they really can't achieve escape velocity. So Earth's gravity is able to hold them down. The moon doesn't have an atmosphere, or I should say it has a very tenuous, a very thin atmosphere. Why? Moon doesn't have an atmosphere compared to Earth. No, it has nothing to do with it. The escape speed of the moon is like 2 kilometers per second. And just about every molecule that's anywhere near the moon is exposed to the sun and is going to heat up a lot. And so basically, all gases are like, woohoo, we're out of here. Jupiter has a ton of hydrogen and helium in it because it's so massive that it can hold on to those gases. Now, our atmosphere wasn't always oxygen and nitrogen. It was a lot of carbon dioxide, a lot of other things. There were biological events that occurred over long periods of time to change the chemistry of our atmosphere. But all of those gases, fluorine, chlorine, nitrogen, oxygen, they're heavy enough, and the Earth is gravitationally attractive enough for those gases to stick around. What the actual amounts are really depend on biology. Venus has a primarily carbon dioxide atmosphere. It's like 99% carbon dioxide now. Venus has a runaway greenhouse effect going on. But the supposition is that Venus probably had a different atmosphere a long time ago before all the carbon dioxide took over. Don't take that as I hate it when people say, well, global warming, look at what happened to Venus. We're not headed there, okay? It takes a lot to get a planet to tip over like that, okay? And by a lot, I mean not only a lot of like energy and other things going on, but like a lot of time to get it to happen. It's not going to happen overnight, okay? When it comes to global warming, we just have to decide how much we're willing to let people suffer through increased temperature, less food production, all those kinds of things, right? The oxygen's not going away. We're going to be just fine when it comes to oxygen, as long as we don't cut down all the trees. If we cut down all the trees, then I'm worried, and I'm leaving on a spaceship. I'm out, okay? So that's like one of my favorite things about the kinetic theory, is that you can calculate these speeds, and you can learn some pretty cool stuff and tie it back in with some of the other physics. There's another result coming out of kinetic theory, which is pretty darn important for where we're going to go next, which is the internal energy. So again, back when I was talking about, we talked about temperature, we talked about total energy, and we talked about heat. So we spent a lot of time talking about heat these last couple chapters. The internal energy, the amount of energy in a gas, is also easily calculated. It's 3/2 N RT. If you know the temperature in Kelvin, and you know how much gas you have, then you know how much energy is in it. That energy, capital U, is the internal, and we call it internal energy. It's internal to the gas, right? It's like the amount of energy that's in it because it's wiggling. Not internal gas, internal energy. If you're disturbed by the fact that 3 keeps cropping up in all of these equations, okay, that comes down to the simple fact that there are 3 ways that molecules can vibrate. What are the 3 ways that molecules can vibrate? Up and down.
Side to side.
Around, and side to side. So 3 degrees of freedom is what we call it in physics. So that's where the 3 always comes from. The half, don't worry about the half. The half is statistical in its nature. All right. We didn't. I glossed over when I was talking about the phase changes and the thermal transfer mechanisms for, like, you know, when something is when doing conduction, convection, or radiation. There are 2 phase changes that take place not at the freezing and boiling temperatures of materials. And those are evaporation and condensation. By definition, evaporation is water turning from its liquid to its gaseous state, but it's doing it not at the boiling point. Your skin evaporates water all the time, depending on the relative humidity of the air. And so your skin's not boiling, okay, when that takes place. Condensation's the other way around, right? Condensation is when gas, vapor, water vapor, turns into liquid. And you'll see this like on windows and all that different kind of stuff, right? Depending on where you are. You can get condensation in the shower, right? As the water droplets form on the glass or the shower curtain. You can experience the difference between evaporation and condensation right now if you just do a simple experiment. Take your hand, so like you want to be, the back side of your hand is actually very sensitive to thermal energy. If you kind of look at the back of your hand, pucker up and blow, just blow across it, what do you feel? It's colder, isn't it? Okay. That you just experienced evaporation. What happened there is that there's water molecules on the surface of your skin. And you had a very fast flow of water molecules, air flowing over the top. And there were some molecules of water in the surface of your skin that were really, really close to becoming gaseous. They had like just enough energy that they could almost become a gas. And when you blew on your hand, what you did is you encouraged all of those water molecules that were just about ready to do it. They took the leap and they left. So what happened to the average energy of the water on your skin if the ones that had high energy to begin with leave? It drops, doesn't it? And a drop in the average feels colder to us. Thermal energy was leaving the back of your hand, and so it felt colder. Okay, same experiment. You're just going to change the shape of your mouth. Okay? Instead of blowing, you're going to, you might need to move your hand closer.
It's warm.
Now it feels warm. By like that, you actually expel air at much slower speed than like that, okay? Those slow air molecules, there's a bunch of water vapor in that air that's kind of sluggish and it really wants to be in its liquid phase. And then it hits the back of your hand and it sees a bunch of its buddies that are all lazy like it wants to be. And so they will turn from gas to liquid. They'll condense on your skin. And since they're bringing energy in, what happens to the average? It increases. And if the average energy increases, we feel that as an increase in temperature. So evaporation and condensation. If you take a shower and you had a nice hot shower and you step out of the shower into a cold room, it feels really cold, doesn't it? What's happening? There's evaporation is taking place, right? So ways to counter that is to dry off before you get out of the shower. There's that horrible moment when you got to reach for the towel, right? Okay. See, there's some things that are common to all human beings. This is definitely one of them, right? That existential dread of having to reach for the towel outside of the shower, because if it's in the shower with you, it's wet. Anyway, it's a problem. We've never solved it, except for heating our bathrooms too high. What do you need to do to cool down in the summer? If stepping out of a warm shower gets you cold because the water on your skin's evaporating, the warm water on your skin is joining its cousins in the air, cooling you down, then we should be able to cool ourselves off by causing evaporation to happen on our skin. So what are some ways that we can cool off in the summertime? A fan. What does a fan do? Blows air, right, onto us, which causes the water on our skin to evaporate. The problem is that a fan only works for a few minutes, because eventually you'll get to a point where the rate at which evaporation is occurring from your skin is exactly equal to the rate of condensation on your skin, and then it just feels like warm air that's blowing on you all the time. So there's a limit to what a fan can do if you reach saturation limit for evaporation and condensation. So what does an air conditioner do for you? It's different from a fan, because an air conditioner has a fan in it. It removes water. Okay? If you didn't know this already, the air conditioner has a condenser in it. And that condenser condenses water out of the air, drying the air out. That dry air is then blown into the room where it runs into your skin, and that drier air with less water in it can continuously evaporate the water off your skin. This is why people say that they dry out when they're under air conditioning, right? Because literally you are being desiccated, right? So counteract by drinking more water, right? But the air conditioner will continue to pull water vapor out of the air to provide a cooling effect, right, for that evaporation that's coming off of your skin. All right, that was chapter 14. It only took, well, it took 50 minutes, okay? No problem. Let's get started with chapter 15. You're like, Mr. Baylor, just let us go. Actually, this means I can do less next week, right? So let's push this while we're here, and let's see how far we can get, and then when I'm done here, I'll make a judgment call as to what's going to happen on like Monday and Tuesday. Because what's happening on Wednesday of next week? You're sick. I'm sick, right? So let's see how sick I can get. well, let's see what's going to happen in chapter 15, how far we get. Because I'll probably have to, I'll need to lecture a little bit to finish chapter 15. I shouldn't record things like this on YouTube. Would you rather come to lab? Would you rather come Monday and not Tuesday, or would you rather come Tuesday and not Monday?
Tuesday and not Monday.
You guys don't have class on Monday. You are not 2B. Never mind. We're going to have to come on Tuesday no matter what. But Wednesday, you're not. I'm going to be sick. Okay, we're good. We're good. Sorry. Here's the problem. For 23 years, Physics 2A has always been at 8 o'clock in the morning. This is the first semester that 2A is at 9:30. So guess which class is at 8 o'clock in the morning? 2B. And guess what I keep telling them? Yeah, that they're 2A. You guys are 2B. That's all there is to it. All right, let's talk about the laws of thermodynamics. Sorry, I was going to give you some good cheer there, but we can't. We're going to have to come on Tuesday because I can't. Actually, I could finish this in 15 minutes, but you guys would be dead. No, it would be awful. There'd be blood on the walls. Okay, so chapter 15, the last chapter.
Wait, is it?
Yeah, this is the last chapter of this semester.
Oh my gosh.
Yeah, it's pretty cool, isn't it? Right? So, pun intended. So, the laws of thermodynamics. I hate these laws. Because we screwed up, there are, can you remember if there's 3 or 4? It might be 4. But they don't start at the first law. They start at the 0th law. Historically, the first and second laws of thermodynamics were known, and then they realized that they needed another law that was more fundamental than the first 2, and so they called it the 0th law. But nobody knows the 0th law of thermodynamics because it's stupid. This is the 0th law of thermodynamics. If you have, let's say, a chunk of metal, A, okay, and it's a certain temperature, and you have a second chunk of metal, B, okay, that is the same temperature as A, and you bring both of those chunks of metal in contact with a third chunk of metal, chunk C, and you let them sit for a while, they'll all have the same temperature when they're done. That overly convoluted, stupid law is the basis for what we define temperature to be. So kind of necessary, right? But not useful at all. It basically is a definition of what thermal equilibrium is. The first and second law of thermodynamics. The first law of thermodynamics is a statement about heat, energy, and work. It reads that if you're going to change the internal energy of a gas, whatever that change in energy is, it has to be the difference between the amount of heat that went into or out of the system and how much work that system did. This is not a new law. I want to be very clear about this. I know you probably, unless you paid attention in chemistry, you've never seen the law written like this, okay? But this law is conservation of energy. It's conservation of energy just written down in kind of a different form. And it needs some explanation because I dropped some terms in there like system and work on the system. So we got to be really careful. Anytime any scientist, especially a physicist, says, I have a thermodynamic system, they are thinking of something very specific. It's a container, and that container has a lid that acts more like a piston. It's like a movable lid that can go up or down. So this lid can go this way or it can go that way, okay? And the lid contains an ideal gas inside of this container, okay? So what's work? When we learned about work way back when, do you remember what work was? Like its definition? It's a really good thing I don't give a cumulative sign on here, right? What was work? Force times distance, okay? So in order for work to happen, There needs to be some force applied to this piston, and the piston's got to move somewhere, right? So what is that doing to the volume of the system? If this piston goes up, what happens to the volume? It increases. If the piston goes down, decreases, okay? So basically work is all about like what the volume's doing. A little bit more than that. We'll get to more definitions in a second. So physicists, we focus on this work because we want to be able to take a thermodynamic system and do something with it. And by do something, that means doing work. This idea is what your car engine does. A gas gets burned inside of a thermodynamic shell, and what does that burning gas do? Pushes a piston, right? And that piston is harnessed to do work. So here's one of the big gotchas that where chemistry and physics differ. Work is positive when the system does work on its surroundings. Work is positive if the piston goes up. So that's what physicists call positive work. Chemists do exactly the opposite. For a chemist, positive work is if the piston gets pushed down. The difference here is a matter of focus. We are arguing over which way is positive. Like, is positive X this way or is positive X this way? In our opinion, physicists, the chemists have gone backwards. Okay, and we've gone forwards. Chemists really don't care about the rest of the universe. All they want to know is what's going on inside of that gas. Physicists could care less about what the gas is doing and wants to know what the effect on the rest of the universe is going to be. So that's really where this kind of conceptual difference is drawn. For you, the student, it's horrible because you now have two different teachers who you may or may not respect telling you two exactly opposite things and you don't know who to believe. They're both right. They're both consistent, right? We're just arguing over which way do we want to call positive. But for this class, for Wiley Plus, for this book, for this teacher, positive work is when the piston goes up and the gas does work on its surroundings. So what is negative work?
Chemistry.
Yeah, chemistry. If the piston goes down. Okay? I believe both physics and chemistry maybe, Q is positive if heat goes into the system. If heat goes in other words, if thermal energy is transferred into the gas, making it warmer, we call that positive. And Q is negative if heat leaves. Okay? So these are important, like the big box here establishes a type of coordinate system when we start talking about the laws of thermodynamics and what's going on in one of these systems. And then there are, I'm going to write it on this screen just because we're going to use it a lot. Right? Notice the top equation, the first law, the conservation of energy equation, is all about a change in energy. That change in internal energy is happening because heat is either going in or out and work is either being done or not done. The actual energy is just 3/2 nRT. Right? So if there's a change in temperature, you can get a change in internal energy, so on and so forth. So it just kind of helps to have the whole toolbox right there. Okay? And then there are different processes that can take place within a thermodynamic system. And there's 4 main ones that we need to talk about, and this might bleed over into Tuesday. Please don't panic. Please don't panic. I know that there's 4 things on the screen, okay? And there's big words. And for those of you that have chemistry, yes, those are PV diagrams. So it's going to be okay. It's going to be okay. It's not going to be as bad as the chemistry version. I promise. I've done both. Okay? A PV diagram is a shorthand visualization for what's going on in a gas. Okay? It's literally pressure and volume on two different axes, right? Where temperature is kind of ignored in the diagram. And what you do is you plot curves to see what's going on. But beyond that, we're just going to use them as pictures and labels, visualizations, to remind us about what's going on. The other big words are big words because scientists feel like they need to assert some sort of dominance over normal people. Okay? So I have defined what all the other big words mean except the last one. Okay? So you might run across an isobaric process. These are Latin roots to this. Baric is the Latin root for pressure, like a barometer measures pressure. Okay? Iso is a Latin prefix that means keep the same or equal. Okay? So isobaric means same pressure. I'm just letting you know, giving you a glossary here. Hopefully the problems that you'll get will just say constant pressure, right? But every once in a while, especially ChatGPT will throw out these complicated terms like isobaric. Okay? Isochoric, this one is definitely one that's probably not on your radar. Okay? Isochoric means constant volume. Okay? Yeah, choric. I can't remember what the actual Latin root is, but it has related to volume. Thermal, isothermal. With your newfound knowledge of Latin, what thermal? Like temperature, right? And then what does the iso mean? Same, even, equal, or constant. Okay? So isobaric means constant pressure. Isochoric or means constant volume. And isothermal means constant temperature. So on a PV diagram, realizing that pressure's on the y-axis and volume's on the x-axis, what would a constant pressure event look like? We need to draw like a PV relationship where the pressure is staying the same. Any guesses as to what that might look like? It would just be a horizontal line. Okay? The pressure stays the same, but what changes? Think of ideal gas law. I should probably have put that over here too. Because the thing that's inside of the system is an ideal gas, right? So if we hold the pressure the same, and in our systems we're not changing the number of moles of the gas, if our pressure remains the same, that means volume and temperature can change, right? Well, remember, this is a PV diagram. We're not looking at temperature. So if the pressure stays the same, but other things are happening, like work and heat and other things, then that means the volume has to be changing. And indeed, it goes from some volume initial to some volume final, right? All right. In a constant pressure process, if we go back to the first law of thermodynamics here, right, where the change in internal energy is equal to Q minus W, okay? In a constant pressure process, the amount of work that's done is equal to the pressure, which is a constant, times the change in volume of the system. Pressure is remaining the same, but this piston is going places, right? The volume is changing. It's either going up or down, right? So that work turns out to be just whatever the pressure is times the change in volume of the system. So what does that mean then, that the change in internal energy is like how would we write down the first law for an isobaric process? Well, that's Q minus P delta V. So it's like, to calculate the work in a constant pressure process, I just take the pressure multiplied by the change in volume, I'm done, right? I can then figure out whether or not the internal energy changed, if heating happened. Like, if this were a pressure cooker on a stove that had a movable lid, you don't want your pressure cooker to have a movable lid, and we started putting heat in, right? What would you expect the volume of this gas to do if we kept the pressure the same? If the pressure stays the same and we start throwing in heat, which is going to raise the temperature, what's going to happen to the volume? It's going to increase, right? So we'd expect work to be positive there. Okay? All right. And the change in internal energy would be whatever the heat that went in minus the change in volume that went out. Seems kind of, I don't know, straightforward. Okay. What about isochoric? Constant volume. What would that look like on a PV diagram? A vertical line. If a constant pressure is a horizontal line, then constant volume is a vertical line, which means our pressure is changing, isn't it? I'll just call the initial down low and the final up high. You can reverse the order here, okay? So if the volume is constant, what is the work going to be? If the final volume and the initial volume are exactly the same, what's the delta volume?
0.
It's 0. So what's the work?
0.
It's 0. Which means that the change in internal energy will only happen if heat is entering or leaving the system. It's actually a pretty easy one, isn't it? That one's not so scary. All right, now it gets scary. Isothermal. So same temperature. On a PV diagram, we don't have a T. Right? There's no temperature on here. So what ends up happening is pressure and volume both change. We have initial volumes and final volumes. We have final pressures and initial pressures. Okay, everything's changing at the same time, and it doesn't change nicely. It's not linear changes here. Okay, unfortunately, the amount of work is equal to nRT times the natural log of V final divided by V initial. Don't ask where it comes from. You don't want to know. Okay? Just accept it. Let it flow in, let it flow out. Move on.
Where does it come from?
Okay. No. Wrong question. Okay? So the work gets nasty. Can you see it? It's like mostly ideal gas law there. Okay? But then we've got to deal with this like natural log that showed up all of a sudden as the ratio of the volumes. It is what it is. However, because the temperature is the same, temperature remains the same. The change in temperature is what?
0.
It's 0. So what does that mean the change in internal energy is?
0.
Also 0. So the change in internal energy is 0. That means, according to the first law of thermodynamics, your work is directly equal to the amount of heat that went in or out. This is what happens in your car's engine, believe it or not. I know it doesn't seem like it because there's a lot of temperature leaking other places. We'll get to that later, right? But we actually try to pull off as close to an isothermal process as possible so that all of the heat that's generated by that process can be turned into work, getting your car to go. And then there's adiabats. Adiabatic processes, by definition, means that heat did not go into or out of the system. So if Q is equal to 0, what does that mean for the second law of thermodynamics? Well, it means, first law of thermodynamics. It means that all of the energy changes that happened in the system were caused by work and not by anything else. An adiabat, this looks weird. An adiabat is the curve that exists between two isotherms. By keeping the heat the same, temperature, volume, and pressure are all changing. Okay? And an adiabatic curve will be the curve that links two isothermal curves. Which one on the screen here is like the worst to calculate? It's isothermal, right? That work, I mean, just arguing with your calculator long enough to get a natural log off, right? A natural log, by the way, is not the log button on your calculator. You realize the difference, right? Because log on a calculator usually means log base 10. And what's a natural log? It's log base E, okay, to the exponential value. So watch out for that. Yeah, this is a picture that's supposed to show all four of them happening at the same time. Basically, it just causes panic in me, right? But I hope you can like see here, right? If you look at this one, you know that's a constant volume process. Not because they labeled it as such, but which way is it going? Perfectly vertical, right? Perfectly horizontal would be the same pressure. The one that follows the isotherm is isothermal. And then the one that's just doing whatever it wants is the adiabatic process. Okay? So just so you have some ways to be able to calculate what's going on in your systems when they tell you stuff like find the work that happens during an isothermal process. Okay? You can calculate it out. It's not terribly difficult. Do realize that you might have to introduce ideal gas law into some of these processes, right? They might not tell you the temperature. They might tell you the pressure and volume. And so you need to use the ideal gas law to calculate the temperature that it's happening at. So always keep that in your back pocket. Let's stop there. Technically, I had 4 more minutes, but we'll give you a little bit of a Thanksgiving surprise. Next week, we are meeting only on Tuesday, right? Yes. Only on Tuesday. I will see you next week.